P8, quarks and antiquarks. Okay, so we've talked about particle accelerators. They, as we've made them over the years, have got more and more energetic, so huge amounts of energy. And what happens to that energy in collisions is that some of it turns into matter. So you typically get showers of particles. Now, some interactions, so some particles were never seen, and there were no obvious reasons for that. Charge was conserved, mass was conserved, or mass energy, but some interactions just didn't happen. So they made up a new rule to account for that, and they invented this property called strangeness. And it turned out it was conserved in the strong interaction, but not the weak. Another thing they discovered with their particle accelerators is that baryons are actually made up of smaller particles called quarks. They have mass, they have charge, and we've now got to add in a third property which we're calling strangeness. An important thing about quarks is that they are never observed on their own. They're always in triplets or pairs. So, this is a picture of what we've got so far. We started off looking at the leptons, so we've got the electron and its neutrino, and we also mentioned the second generation of electrons, which is the muon and its neutrino, and we've briefly talked about the three forces: the strong force, the electromagnetic force, and the weak force. Now, all normal matter only needs these four particles: up, down, quarks, the electron, and the electron neutrino. And the neutrino doesn't exactly impact on our lives very much. So pretty much the three most important particles for us are the up quark, the down quark, and the electron. Now that's an incredibly simple picture. But when you start using particle accelerators, say some of the energy can turn into matter, the next most common particle to form is a strange quark, and that's part of the second generation. Okay, so we're only going to be interested in things that you can make out of these three quarks. There are obviously lots of other possibilities if you include all six quarks. So here's a table of quark charge and mass. If you look down at the masses, you can see they get more and more massive as you go further and further down. And there's a big jump from the up and down quark to the strange quark. That's about 50 times more massive. But the charm quark is more than 10 times more massive than that. So that's why the strange quark was seen first. It was easier to produce than the others further down the list. In this table, we've also got the electric charge, which, as you can see, comes in either thirds or two-thirds of the charge on an electron. And here we've got the generations. So up and down in the first generation, strange and charm in the second, bottom and top in the third generation. So we're just going to be looking at the top three. So the rules are, if you want to make some particles, charges must add up to an integer multiple of E, the charge on an electron, or 0, if you count 0 as an integer. So baryons are particles made of three quarks, and mesons are made of a quark and an antiquark as a pair. So let's start with baryons. Remember, we're just looking at the first three quarks, up, down, and strange. So the most common baryon, and indeed the most stable, is a proton. It has a charge of +1, which means it must be made of a +2/3, a +2/3, and a -1/3 makes 1. That's an up, up, and a down. So proton is an up, up, down combination. The next most common, a neutron, has 0 charge, and you can make that with an up and 2 downs. So 2/3, -1/3, -1/3, and that works. What they also saw in particle accelerators were things called sigma particles. And it turns out the sigmas have one strange quark. They can have 0, +1 or -1 charge, and you can make them just by swapping one of the quarks in a proton or a neutron for a strange quark. So you can have up strange, down strange, or down strange. And they fit the bill as far as integer amounts of charge is concerned. So they're the possibilities. And just to remind you that all those particles could have antiparticle versions. So basically double everything there. Mesons, on the other hand, are the quark-antiquark pair. So perhaps the most obvious ones are to have an up anti-up, a down anti-down, and a strange anti-strange. They are all called pi0 mesons, or pions. You could then have a down anti-up, or an up anti-down. If you use the table that's on the formula sheet and count up the charge for this one, you'll find that it comes to -1. So that's a pi minus. Whereas this one is actually the opposite and comes to pi plus. Excuse me. We could then have a down anti-strange or an up anti-strange, and that would give us the K0 and the K plus mesons, or kaons. Strange anti-up and strange anti-down give us K minus and another K0. So there are lots of patterns here. There are 7 particles. They represent all the possible combinations of up, down and strange and their anti-versions. These two both have a down. These two both have an anti-down. These two both have an anti-up. And these two have an up. These two have an anti-strange, and these two have a normal strange. So they're every combination possible. You might also notice that if you go across the hexagon, the pairs of particles formed that way are the antiparticles of each other. They're the complete opposites. So these are the mesons you need to know about: pions and kaons. The way I remember which is that the K particles are the ones with the strange particles in them, with the exception of this one. So strange anti-strange is actually a pion. But all the others, which have a strange or an anti-strange in them, are Ks. So I think of special K, as in the breakfast cereal, S for special, S for strange. Okay. Strangeness is conserved in the strong interaction. So, for example, when these massively energetic collisions produce new particles, then strangeness has to be conserved. But it's not conserved in weak interactions. So when strange particles decay into normal particles, you don't have to conserve strangeness. It can just disappear. Okay? And just to be a little bit awkward, a strange quark has a strangeness of, wait for it, -1, not 1. But in your formula sheets, you'll see the strangeness of all the particles is listed in a table.